Hello, everyone. Back again for Chapter 7. This chapter is from our GOB or Chem 51 class. The topic of the chapter is energy and chemical processes, and the contents of this lecture are energy and its units, heat and temperature, phase changes, bond energies and chemical reactions, and a quick look at energy of biochemical reactions right at the end. So without further ado, let's go. Okay, so energy in units. So what is energy? Close your eyes, try and imagine what a bicycle is. You probably have some image in your mind. Two wheels, might different materials, but definitely circular in shape. Some kind of frame, handlebars, saddle, etc. Now close your eyes and imagine energy. I'm imagining it's a lot more difficult for you. And that's because the bicycle was easy on the one hand because it's a noun or a thing, an object. But energy is not really a noun. It's more similar to a verb. So you imagine something that has energy or can do something because of energy. So that's why it's harder to think about energy. So energy, if you look at the top left here, from any textbook, you'll hear in the definition of energy that it's the ability or the capacity to do work or transfer heat. So whatever energy is, if you have it, you have the option of doing something with it, doing work, transferring heat. And that's probably as deep as we can go in this class. We can't create or destroy energy. So there's a concept of conservation of energy, similar to conservation of mass. And what that conservation law means is that you can't create or destroy it, but you can take it from one form to another, or it can be transferred from one form of matter to another form of matter. So we can transfer it from one object to another. And if the transfer of that energy between the objects is because of different temperature, we call that particular energy heat. So heat is the transfer of energy from one part of the universe to another part of the universe because of difference in temperatures. And here, universe literally means anything. Okay, so looking in the middle here, we have two common units of energy. They're not the only units of energy, but they're the common ones in chemistry. We have the joule, named after James Prescott Joule, and that's the System International unit of energy, work, or heat. And exactly 4.184 joule is equal to 1 calorie. A calorie is a unit of energy. Now, it's not to be confused with the food calorie. So the calorie that you and I see on our nutrition labels, that's actually 1,000 of these calories. So the food calorie is an uppercase capital C calorie. These lowercase c calories are 1,000 times smaller than those. Okay, so this type of table is never to be memorized, but just to spur conversation. So you can see the type of exercise that you might do and the energy expenditure per hour that you might exert. Now here we can see that we do indeed have kilocalorie. So these would be the nutritional food calories. So this would be 320 food calories if you do some low-level aerobic exercise. If you were going to do some yoga, 280 food calories. If you're just going to walk up some stairs, over 1,000 food calories. Okay, so heat. As we've just said, heat is the energy transfer between two objects at different temperatures. Heat always travels from an object at higher temperature to an object at lower temperature. So for example, if you assume that your body temperature, we can see down here the second to last row, in Celsius is 37 degrees Celsius. If you put your 37 degrees Celsius on a piece of ice, let's say the ice is at 0 Celsius, then heat will travel from your hot 37 degree hand to the much lower 0 degree ice, And your brain recognizes that as a loss of heat from your hand. So your brain experiences cold by really the loss of heat as it flows from an object at high temperature to low temperature. Consequently, that heat could melt the ice. Vice versa, if you put your hand next to a warm fire, then presumably the warm fire is at a higher temperature than your 37-degree hand. So you would then feel energy enter your hand from the hotter object. So in that case, your hand acts as the cold object because the fire is much hotter than your hand. And your brain encodes this gain of heat energy. So because energy can either be created or destroyed, the energy that flows can be measured either as it enters the colder object or as it leaves the hotter object. Again, this table is merely just for conversation. Nobody's going to ask you what the difference in temperature between a bird and a cat is. Okay, so similar to general heat, there's something called specific heat. Now, specific heat are constants. They are intensive properties. That means they are independent of sample size. And that makes them a constant. And because they're a constant, they can be used to identify an unknown. So for example, aluminum here has a specific heat, here labeled lowercase c, in units of calories per gram degrees Celsius. That means aluminum, for every gram of aluminum that you want to increase its temperature by 1 degree C, you have to give it 0.215 calories of heat. We come right down to the bottom here. Water in the liquid phase has a specific heat in these units of 1 exactly. So if you wanted to raise the temperature by 1 degree C for 1 gram of water in the liquid phase, you would need to add exactly 1 calorie of heat. So how does specific heat relate to heat? Well, if you look at this equation down at the bottom, heat over on the left side of the equality is proportional to specific heat over on the right side of the equality. Here, M is mass, and delta T is the change in temperature. So if we were to solve for specific heat, you can see where the 3 units come from. We have heat as a numerator. If we bring mass and change in temperature down to the left side as a denominator, you can see where the gram and degrees Celsius denominator units come from here. If we look at this cartoon here, this is comparing gold with water. Now, gold, I actually don't see on here, but no, I thought I did. But we can kind of imagine what it would be like, because we can see that the metals, we can see mercury as a metal, value much lower than water. Iron, a metal, value much lower than water. Copper is a metal, aluminum is a metal. So just on the brief overview of specific heat values here, we can see that metals tend to have a specific heat value much lower than water. And that's seen over here on the right. So for a given mass of this material, so either 1 kilogram of gold or 1 kilogram of water, we heat both samples, and the goal is to see how much heat is needed to raise this given mass of the material by 1 degree Celsius. And we can see that a lot more heat is needed to go into the gold than, so this cartoon here is supposed to represent the scale on a heat device were that to exist. But you can see that a lot more heat is needed to go into the water to raise its temperature. A lot less heat is needed to go into the gold to raise its temperature. So as you can see, the heat needed is proportional to specific heat, as we could see down here in the equation. because heat and specific heat are both numerators on either side of the equal sign, so they have a proportional relationship. Okay, phase changes. You can cause a phase change by receiving or losing heat. So when we say phases, we mean solid, liquid, and gas, or states of matter. And a phase change we've seen in a previous video is a physical change, because certain properties that occur during phase changes, like melting point and boiling point, are physical properties, which remember means they can be measured without permanently changing the material. So we can melt, for example, solid ice to give liquid water and reverse it again by freezing it, and we haven't permanently changed the water. We can repeat this process without chemically changing the water. So we can induce these, we can cause these physical changes by adding heat. Obviously, if we add heat, we would first melt and then boil. If we remove heat, we would first condense and then freeze. If we have, so there's a little bit of language here. If a process is isothermal, then we would say that that process happens at constant temperature. So here, thermal means temperature and iso means the same. So an isothermal process occurs at constant temperature. Some other important labels here: enthalpy of fusion, or the heat of fusion, and enthalpy of vaporization, or the heat of vaporization. So these two items are the heat needed to cause melting in the case of fusion. So fusion is the academic word for melt, and vaporization is the academic word for boil, or to change from the liquid to the gaseous phase to form a vapor. If we went backwards, if we condensed, it would just be minus enthalpy of vaporization. And if we froze something, it would be minus enthalpy of fusion. So we keep the same label, we just add a minus sign if it were going in the opposite direction. These can also be called latent heats. And that's because they sometimes are hard to detect. So a latent heat, it typically refers to a phase change. And we'll see, I think, in the next slide. Yes, in the next slide, that a latent heat has no dependence on temperature, or it doesn't cause a temperature change. So let's see what I was going to say here. Yeah, so these last few bullet points just say, you know, if we add heat, we go from the solid to liquid to gaseous phases. If we remove heat, we go in the opposite direction. And then finally, this piece of vocab at the bottom, sublimation. This is when a phase goes from the solid to the gaseous phase directly without first going through the liquid phase. It's kind of like you bypass the liquid phase. So that's just a definition for now. Okay, on this slide, we have some values for this enthalpy, these latent heats, the enthalpy or heat of fusion, which is when you melt, and the enthalpy or heat of vaporization, which is when you boil. And we can see a profile plot graphed out here that plots energy on the x-axis, the horizontal axis, and temperature on the y-axis or the vertical axis. So if we look at this diagram from the left, we see that we add energy to the system, and as energy goes in, heat goes in, if you like, the temperature starts to increase. So we can have a solid material, but it will increase its temperature. And this is because the energy we're adding is essentially being converted to kinetic energy in the material. So we can add heat energy, and because of conservation of energy, that heat is converted into another form of energy. And in this part of the graph, it's converted into kinetic energy. Kinetic energy is the motion of the molecules. At the melting point, which I'm hovering over with my cursor now, so the leftmost part of the melting point horizontal line, that's the melting point. Suddenly the energy keeps going in and something is happening, but rather than change temperature, we're just changing phase. We're melting from the solid to the liquid phase. So during this grayed out melting region, we have a mixture of phases. We have a solid and a liquid phase. And whilst we have a mixture of phases, we can't change the kinetic energy of the material. All we can do is change the potential energy of the material. And it's this potential energy that's changing, that's causing the phase to change from a solid to liquid. So because potential energy is not proportional to temperature change, we see no change in temperature. And this gives rise to the fact that this melting temperature is a constant temperature. Hence, we have a melting point. At some point over here on the right side of the horizontal line, we end the melting point transition. And this means that all of the molecules are now in the liquid phase. Once that's the case, we can again start to raise the temperature of the liquid, and we again go back to kinetic energy, so a transfer of heat energy directly to kinetic energy, which is proportional to temperature, and so we increase the temperature of the system. Again, once we reach this leftmost part of the vaporization horizontal line, this is the boiling point. Again, we're going to start changing phase. We're now going to have a mixture of liquid and gaseous phases simultaneously. So we can't, during this phase transition, we can't increase the kinetic energy. We can't change the temperature. We instead just break intermolecular forces between adjacent molecules. And this is a potential energy phenomenon, has no dependence on temperature. So temperature is fixed, and we can talk about a boiling point. Once we have 100% phase transition all to the gaseous phase, we can again start to increase the temperature of the gas, and we again convert to kinetic energy from our original heat energy. Looking here, is there anything I particularly want to point out about these enthalpies? Yes, we can definitely, you can interpret these. I'll interpret the water one with you. So we notice that the enthalpy of fusion has a reported value of 79.9 calories per gram, whereas the enthalpy of vaporization is much larger at 540 calories per gram. So why is that the case? Well, to melt, we just have to increase the kinetic energy enough so that we can overcome the intermolecular forces binding the solid together so that the molecules can slip past each other in the liquid. The reason why the vapor enthalpy of vaporization is much larger, we have to completely separate molecules from each other, and this requires a lot more energy than just allowing them to slip past each other. We've got to completely remove them from each other at greater distances, and this requires more energy. And you can see this general trend for the vaporization heats versus the fusion heats. Okay, in this slide, we're going to look at bond energies and chemical reactions. So here we have some bond energies listed. These are not some things that you'd have to memorize. If ever you have to calculate an enthalpy based on bond energies, the bond energy values will be provided to you. Okay, so we have an equation here. So we have ethanol plus 3 lots of molecular oxygen. You have 2 lots of carbon dioxide and 3 lots of water. We've now redrawn the equation, but we've exposed each bond. So methanol has this full structure here. The 3 oxygen molecules each have this double bond as shown. The 2 carbon dioxide molecules have this double bonded structure as shown, and the 3 water molecules have this single bonded structure as shown. So if we want to calculate the heat of this process or the heat of this reaction, which is a combustion reaction, so it's an exothermic reaction, and we are expecting an exothermic reaction to have a negative value because energy is leaving the chemicals or exiting the chemicals. So the chemicals experience a loss of energy, so we'd expect a negative sign. So we essentially want to follow this formula. The enthalpy of this process is we look at all the bonds that have to break and add up all their energies. And then we look at all the bonds that have to form when we add up all their energies, and then we just add them all together. So we can see here, if we look at this calculation, so 413 is the first number. So this is the CH bond. So in ethanol, we're going to be breaking these bonds. So we've got 5 CH bonds in ethanol. So we have 5 lots of the bond energy for a CH bond. Plus, we have 1 carbon-carbon bond. Well, that has a value of 348. So we add that. Then we have a value of 360. So where is that 360 coming from? That 360 is, where is that 360 coming from? The CO, I think that might be a typo. We'll come back to that 360 in a second. I'll double check that number. This 463 is the OH bond. Okay, that's the OH bond. Yeah, I think that 360, that's supposed to be the CO bond, right? I'm pretty sure that is meant to be the 743. Okay, I'll double check the calculation in a minute. But essentially, we want to add up all the bond energies of ethanol. Then we've got this carbon-oxygen double bond. Now I need 3 of those. So the the oxygen-oxygen double bond is 498 kilojoules per mole. I need 3 of those. So I add that. And then the bonds that form are going to be these ones over here. So the CO2, I've got CO bonds, but I've got 2 of them. The minus sign here is just because anytime we form a bond, imagine your hands come together and they release energy. Whenever elements come together, they release energy. So bonds that form always have a negative value for their energies. Bonds that break, they require energy to break them, so they have a positive value. So when we take these 4 carbon-oxygen double bonds, each with a value of 743, we just add a negative value here. And then finally, we've got this 463 value, which is the OH bond. Each water molecule has 2. I've got 3 water molecules. So that is 6 total. Okay, yeah, so this 360 looks like a typo. It should be that CO, but it should be 7. No, let's see. Yeah, no, it's the right number. So where it says 743 here, it should say, let's see if I can write over it. So this number should say, yeah, so this number here Gray, I wouldn't have picked gray. Maybe black. I guess that's as black as it would go. So that number should say 360. Yeah, that number should say 360. Let's type it 360. Let's make that red. Live video, folks. That should be 360 there. Maybe I'll give it a white background. Oh, anyway, if you're watching this video, I think that's pretty clear enough. Okay, so again, all the bonds that break are positive values because it requires energy to break them. All the bonds that are formed are negative values. It requires energy to, it releases energy when they form, just like when your hands form a bond, they release sound energy. Add everything together and you get negative 1030 kilojoules per mole. So indeed, it's exothermic. It generates a net loss of heat energy symbolized by the negative value. Okay. So I guess we can play that in. Okay, bond energies and chemical reactions. There are two types of chemical reactions, either exothermic or endothermic. On the left, we see the exothermic. So if we plot potential energy on the y-axis against the progress of the reaction on the x-axis, an exothermic reaction has the products with a lower energy than the reactants. That means, as you can see by the difference between reactant and product energy, symbolized as a red arrow here, there's a net energy release, and that release into the environment is a loss with respect to the chemicals themselves. So the chemicals report a negative value of heat, and that's what we saw in the previous slide with the negative value of heat in the exothermic process. We won't discuss it that much here, but this hump that's needed to overcome before the reaction proceeds is called the activation energy. We might mention that a bit later in the course, but not really at this point in the course. Okay, in contrast, an endothermic reaction is when the products have greater energy than the reactants. So we have a net energy input into the products. So if we look at these two cartoons on the top right here, an endothermic process, energy from the environment enters the system. So for example, an ice cube will melt because energy is entering it on the assumption that it has a lower temperature than its environment, and energy always flows from a higher temperature to a lower temperature. So if you're a lower temperature like an ice cube, energy will enter you, and that would lead to melting of the ice. That's an endothermic process. Exothermic, here there's a fire. Assuming the fire is hotter than its environment, energy would exit the fire. So whenever something generates heat, you would use the left profile and call it exothermic because energy exits the system. If ever something gets cold, then you would use the right profile because energy is entering the system, enter the system endothermic. Okay, these last couple of slides, we're just going to look at some energy of biochemical reactions. So, for example, we have three major energy sources in our diet. So we have carbohydrates. An example here is glucose. So carbohydrates or sugars, they have approximately 4 kilocalories per gram of energy. Proteins are approximately the same energy content as carbohydrates, about 4 kilocalories per gram. And fats are approximately double the energy content of the other two, so approximately 9 kilocalories per gram. So We won't dwell too much on why this is the case, but what we want to mention here is, for example, how we can use this energy content to leverage, or how we can leverage this energy content of our food, not only to give us energy, but to fuel the energetic processes in our bodies. So, for example, the way we have evolved to do this is we convert the energy of our food into a molecule called adenosine triphosphate, or ATP, which is converted to adenosine diphosphate, or ADP. So if you look at the cartoon on the right first, we can see adenosine triphosphate is the structure here. And it decomposes, releases energy to give adenosine diphosphate by essentially spring-loading away one of these phosphate groups. If you look closely, you can see that each phosphate group is negatively charged. So the source of energy of ATP is in electrostatic repulsion between these adjacent phosphate groups. So one boilings off, and we're left with only two, which, although still has energy, is much lower than having three groups of negatively charged structures adjacent to each other. Let's say biologically we want to form a bond between glucose and fructose to make sucrose. And let's say that this costs, it costs some energy. Here we've got units of Gibbs free energy, but the important thing for us is just that it's called energy, not specifically what type of energy it is. So there's an energy bill that we have to pay. And if nobody's going to pay for that energy, the bond won't form. So we can couple this biochemical process to ATP. So if we just look down at the bottom here, ATP will convert to ADP with the loss of energy. And that energy in the same units here is minus 7.3 calories per mole. Here it's negative because it's being lost from the chemical. And conversely, with the reaction up at the top, it's a positive energy requirement because it needs to be added to the chemical. So if we can see by looking at these two values that the negative 7.3 is larger numerically than the 5.5. So if we could gain 7.3 units from ATP, we could pay off 5.5 units to form a sucrose molecule. And that's exactly what happens. We couple them together biochemically, and if we take both overall, we subtract the 5.5 from the 7.3, and we're left with a net negative 1.8. So provided that we're always releasing energy, then the chemistry, the biochemistry will happen. And here we are indeed releasing 1.8 units of energy. So we can use ATP to synthesize sucrose. So that's a small example of how we can leverage energy to make compounds biochemically. And that concludes this video.